Hey everyone, and welcome to Jay's Gaussian. And today I'll be going over the Klein-Gordon Equation, which is a relativistic quantum mechanical equation that describes spin-zero particles. And so we're going to go over that. And usually that's one of the first equations that you learn when learning quantum field theory. And what we're first going to do is go over the Schrodinger equation and then jump into the Klein-Gordon equation. So as per the Schrodinger equation, so as many of you know already, the Hamiltonian for a one photon system, single particle, non-relativistic, is the following. So you have your kinetic energy of a photon and you have your potential energy function. And but you can substitute your Hamiltonian and your momentum for these operators, and you can turn these into operators and make these following substitutions. So the Hamiltonian goes to this operator, which is I h bar. So that, and then the momentum goes to the following. Right. So now, as you can see, directly by substitution, this gives you the Schrodinger equation, and you can see that operating on the wave function, we can immediately get the time-dependent Schrodinger equation just by substituting. You can do this out by yourself, literally just a little bit of algebra, and so that gives you your time-dependent Schrodinger equation. Yeah, so I guess I also have to write. Right. So there you go. So yeah, so all we have to do necessarily is to substitute these operators into the relativistic Hamiltonian, or the relativistic energy. And so particularly what we'll be doing is substituting into the following equation. So this is your time-dependent, let me just highlight this first, time-dependent Schrodinger equation. Let's make like a boundary and switch colors. So in order to describe relativistic particles, to get a relativistic wave equation, we consider the equation E squared is equal to m squared c to the fourth plus p squared c squared. So this is your energy of a relativistic, this is your relativistic energy, right? Relativistic, yeah, right. So here we can substitute all our operators and see what we get. So let's first take the square root of both sides. And so what we get is that I h bar, a partial of the wave function, with respect to t, is equal to negative h bar squared, c squared, times the Laplacian, plus m squared, c to the fourth, that to the 1/2 power, operating on the wave function. So there are some things that don't really make sense with this. For starters, why is the Laplacian under this square root? So how do you even define that? So rather than leaving it with this square root, we're just going to square both sides again and see what happens. And so that gives us negative h bar squared partial respect to t, second derivative with respect to t of the wave function is equal to negative h bar squared c squared Laplacian plus m squared c to the fourth, operating on your wave function. Now we're almost there. We're basically there. We can feel it, because all we have to do for now is to substitute h bar and c with 1. So we just underline all of them, and we get h bar is equal to c is equal to 1, and this is known as natural units. So we are defining units, we're defining a specific set of units such that h bar is equal to c is equal to 1, and those are called natural units. Right. So that's important, because therefore we can make this substitution. So therefore what we get is, we get that negative second derivative of the wave function is equal to the negative Laplacian plus, or let me drag this over here, plus m squared times phi. And so, combining everything, we get that the second derivative of the wave function minus the Laplacian, or wait, not of the wave function, just this operator minus the Laplacian plus m squared operating on the wave function gives you 0. But wait, there's more. Because what we can do is we can make this the following substitution. We know that, so we can take this operator, this operator del squared. And so this operator, what happens is that we're basically making the contraction in the following way. And so what this is basically doing is that we're taking the metric tensor and we are expanding this, and this is just a classical contraction with the metric tensor. And obviously we know that in this metric we're using the Minkowski metric tensor, which is just obviously plus 1, minus 1, minus 1, minus 1, everything else is 0, right? So in that case, doing this matrix multiplication out, we obtain exactly what this is. See, the plus is the time component, everything else is minus, which corresponds to this Laplacian. And so therefore, we can substitute the operator into the equation and get the Klein-Gordon equation. And that does it. And so that's your Klein-Gordon equation, and that's all that is. But let me just say, there are many different problems with this Klein-Gordon equation, and although it fits pretty nicely into, it fits pretty nicely into the equations that we have, there are a ton of problems with it. And actually, there's a paper that is filled with all the problems of the Klein-Gordon equation, and I'll leave that in the description. And if you have any more questions, feel free to leave one in the comments, and I'll take a look. And have a good day. I'll see you next video.